Sì.
It's a pleasure to introduce Bruno Mera, who is a postdoc at the Mathematics Department in Técnico, and he will be talking about information geometry and the analysis of phase transitions.
Thank you very much, Miguel, for inviting me, and thank you everyone to come. So, as Miguel said, I'm going to speak about information geometry in the analysis of phase transitions. So, let's go to the outline. So, I will begin by talking about geometry and state distinguishability in quantum mechanics. I will mention this notion of gauge ambiguity. And then I will talk about fidelity, which is a central quantity from which a lot of geometric quantities can be derived from, and the Uhlmann connection and the relation to phase transitions. Then I will focus on two papers that with the associated results. The first is the fidelity and Uhlmann connection in free fermion systems. Namely, we will study, we will explore topological phases, such as the Kreuzleider model, and also the BCS theory of superconductivity. Then we also studied, using this approach of the fidelity, dynamical phase transitions, which is something which is quite hot right now, and namely at finite temperature, and using this approach of fidelity and the associated geometric quantities. Okay, so let us begin. So, in quantum mechanics, as you probably all know, a pure state is a ray. There is a one-dimensional subspace of a Hilbert space. And as such, if I consider a normalized state, there is a U1 gauge degree of freedom that allows me to choose different representatives for the same state. And if I want a gauge invariant description of the state, I can use the orthogonal projector. And the state itself is identified with the image of the projector. More generally, we can have dimension k linear subspaces of the Hilbert space, and then I have a U of k gauge degree of freedom in defining this subspace. Again, we can have a gauge invariant description through the orthogonal projector, and this generalized notion of state, which is a projector, a particular class of density operators, is in one-to-one correspondence with the image of this projector. Okay. So if there's a gauge ambiguity, is there a gauge field? Yes, there is one choice, because we're dealing with Hilbert spaces and we have an Hermitian structure. And this choice is called the Berry gauge field or connection. It can be abelian or non-abelian, depending on the case of having a pure state or the former case. There is also a metric, which some people call the quantum metric, but in math it's called the Fubini study metric, because we have a projective space. And in the more general case of density operators, it is the Beer's metric. And if you fix a rank of a density operator, this is well defined. Okay. Okay. So let's consider the simplest example, so I can show you this structure. So we have a principal bundle of normalized vectors in Cn to physical states, which is the Cpn minus 1. And this is just a cartoon showing that for a given state, I can choose different representatives of the state. Okay. So the Berry connection upstairs, it is an Ehresmann connection, and it is represented by this differential one form with values in the Lie algebra of U1. And it is simply given by applying the exterior derivative to psi and then projecting with psi again. And of course, as an Ehresmann connection, this splits tangent vectors into vertical and horizontal components. The vertical directions are predetermined, but it allows you to define the horizontal directions. So directions in which the state is actually changing. And the metric tensor is simply you take this variation of psi and you take out the vertical part, which is given by that. Okay, and this is essentially, for those of you who know, this is the Fubini study metric in CPN-1. So I'm going simpler and simpler. So for n equals to 2, the space of states is called in quantum information the Bloch sphere. And then I will also talk about its spin 1/2 coherent states. So here we have the space of states to be the Riemann sphere, and the Riemann sphere has coordinates given by stereographic projection with respect to some pole. And the physicists usually choose as representatives for the states these states of this form. Okay, essentially, of course, you cannot choose in this formula. You cannot choose z equals to infinity because this becomes ill-defined, and this just shows that what you're doing is to choose a local section of a line bundle. In other words, right? So this coherent, these spin 1/2 coherent states define a local section of a non-trivial line bundle over S2, which is essentially the tautological bundle. And in physics, we also call it the monopole bundle. And I will explain later why. There is, of course, the relation of these states with the Bloch vector, that is the point on the sphere we're talking about, and this is just obtained by taking this observable, which is that of the Pauli matrices. I'm sure you know what Pauli matrices are, right? So,
what do you mean here? Any Pauli matrices, or
here you consider the vector of all Pauli matrices, and then each of the components. So if you want, this is essentially how you project in the line bundle. So you have the section. Something like this, and by applying that, you get the identity, right? To describe the full space of states, of course, you need another trivialization valid in the neighborhood of the south pole, because I chose z cannot be infinity within this description, and then you take another coordinate, which is the inverse of z. And then you see that modulo gauge transformation, you have this state here, which is now well defined for w equals to 0, which means z equals to infinity. So the difference between these two sections, wherever they are both defined, is a U1 gauge transformation. And this is a manifestation of that gauge ambiguity that I was talking about. And the subtlety arises because this bundle is non-trivial. It is actually a generator of the abelian group of line bundles over the sphere. Okay, so then you can take the pullback of the Berry connection, and this gives you this local differential form here. And the metric in the space of states, if you write it in terms of that coordinate z, is simply given by that, and then you find that this is 1/4 of the usual round metric in the sphere, and this implies that you can think of this space of states as a sphere of radius 1/2. Okay. The Berry curvature is given by the exterior derivative, and it is given as such. And if you take the metric and the curvature together, they form the so-called quantum geometric tensor. It is actually a Kähler form, right? And this, you see that this description encompasses both objects. And of course, you can integrate this curvature in the sphere, and you get a topological invariance, which actually defines a twice isomorphism, the line bundle that we're considering. And here it is this number, which is -1. Okay. So more generally, physicists have been interested in these symmetry-protected topological phases of free fermions. And in that case, we suppose that we have, for me to give you an idea of what I'm doing now, suppose that I have fermions on a lattice, say Z2, and at each point, at each point of the lattice, I have two flavors of fermions. And then what happens is that if you have translational invariance, you can go into momentum space when you have a quadratic Hamiltonian, and it goes, it is essentially, the system is essentially described by a Hamiltonian like that. Okay, cool, let's bring this one. The system is described by a Hamiltonian like that, where K is the momentum. But of course, since you are on a lattice, momentum is only defined modulo 2 pi, okay? Because you have these lattice translations, and then you have to, you're instructed to identify K by reciprocal lattice vectors, which are of the form where m and n are integers, okay? And this, what it tells you is that the space of all momenta is topologically a torus. This is the first Brillouin zone of an insulator, okay? And if you have a gap condition, meaning that this vector d of k is non-vanishing, then everything becomes well-defined, and you can pull back the structure that you have on the sphere, meaning the non-trivial line bundle, through the map that is given by d of k divided by its norm, okay? So essentially you have a map from the torus to the sphere, and you pull back all the structures that you have on the sphere to the torus. That's it. So physically, the ground state of the theory is obtained by filling the lowest energy band, which, because of the gap condition, forms a line bundle over the torus. Okay, this is what I was trying to tell you. So if you do the calculation, you understand that these eigenstates of the lowest energy band can be written as these spin coherent states. For those of you who know, Z going to -1 over Z bar is simply the antipodal map. And this locally describes L, of course, whenever this is different from infinity. So again, this is what I was trying to tell, that L is the pullback bundle of the monopole bundle. And the first term number of L is nothing but the winding number of this map that I just described, which is the natural thing. So if I have a map phi defined by this from the torus to the sphere, and I pull back the line bundle here, the first term number of this line bundle is simply the winding number of phi. Yes?
This argument of this previous slide and this slide that
yes.
lower because I'm getting.
Oh, sorry. Here?
Yeah, from
okay, so let me explain a bit in detail. So you have a Hamiltonian, which is simply a 2x2 matrix for each k. So in other words, I have a family of 2x2 matrices parameterized by a torus, okay? And then this family is subject to a condition, which is a gap condition, which can be stated in terms of the non-vanishing of this vector d, okay? D of k is non-vanishing for all k, okay? And again, what I'm telling you is that for each k, so in fermionic sense, if you have a structure like this, the ground state is obtained by filling all these states here. So as a function of k, you have states which are below the gap and states which are above the gap. Those states that are below the gap, they are the eigenvalues of this Hamiltonian, which have negative eigenvalue, the eigenvectors which have negative eigenvalue. And essentially, the collection of all these subspaces forms a vector bundle, a line bundle over the torus, okay? And this line bundle is actually the pullback bundle of the bundle that I described before, the monopole bundle, by this map, which is obtained by giving to each k this normalized vector on the sphere. Is it clear?
Yeah, but the Hilbert spaces.
The Hilbert space is more complicated than this. This is the single particle Hilbert
This is
space.
the single particle.
Exactly. Because the Hamiltonian is quadratic.
The Hamiltonian is quadratic.
So it is free. Oh, sorry, I cannot go there. I forgot that big part. So let me put it in better terms. So the theory is described like this. So you have a Hamiltonian.
So this is a free pair.
Yes, you have a Hamiltonian like this. Where this is each of these guys has two fluid flavors, okay? And because of translational symmetry, you can go into momentum space, and that means that you can transform this into a sum, an integral in the torus of something like this, where this is a 2 by 2 matrix, which can be written in that form that I wrote there, d of k dot sigma, okay? So a linear combination of Pauli matrices, or of generators of SUT. And then what happens is that because of the gap condition, you have energies which are below the zero and above the zero. The zero is a convention, so I can shift it. It's the Fermi level, basically. And essentially, the ground state is obtained by creating over the vacuum all the states that are below the gap. Okay? What I'm saying is that the collection of all these states labeled by the momentum is a line bundle, which is the pullback bundle of that monopole bundle that I had there. Okay? And it's called the monopole bundle for, I'm sorry, I forgot to say this, because it corresponds to a constant magnetic field on the sphere. And if you extend it to R3 minus the origin, it corresponds to a monopole centered at the origin. This is the detail I forgot to say. So is it clear right now?
Yeah, more.
It's a line bundle over the torus.
Over the torus,
Okay,
yes.
Yeah.
It's the Brillouin zone is a torus, okay? So this is what I wanted to say. And then let us move on to the fidelity, which is kind of a central notion in all this framework. So fidelity is something very simple. It is an information theoretic notion, a measure of distinguishability between two quantum states. Let's say, roughly, whenever a phase transition occurs, the state of the system changes dramatically, and the fidelity will also capture this change. So this is very hand-wavy, but let me do it more precise. So for pure states, it's simply this naive overlap. It's something quite trivial. But suppose that I have a family of ground states of a given Hamiltonian, parameterized by the same, by some topological space, let's say. Then I would like to, this would be the ideal object I would like to study. So the fidelity between the ground state at a given parameter and a parameter which is perturbed a little bit. Okay. Generically, if everything goes well, this should be close to 1, because as the states go closer, this overlap goes to 1 if they are normalized. But whenever there is a phase transition, there will be a sudden drop in this, and I will show how this sudden drop can arise, okay? Right now it seems very sketchy. And the reason why we'd like to study this subject is that it then allows us to probe quantum phase transitions.
So you are looking at points where this is not differential.
Exactly. So what happens is that the first derivative is trivially zero, but the second derivative, which is in physics a susceptibility, it can become singular under certain conditions, and it's in that regime that you have quantum phase transitions. Okay, you're going to the next slide. So you define this susceptibility, which is the second derivative of this. And whenever there is a quantum phase transition, in the thermodynamic limit, this diverges, okay? But, and in fact, this quantity here, we will see that it is actually intrinsically geometric. It is related to the metric that I described before. Okay, so let me go a little bit. So the Berry phase in physics is essentially related to the parallel transport with respect to the Berry connection, okay? And I will show you now that there is a relation between this Fidelity object and the Berry phase, and this is easy to see. So if I take a curve of states like that, or normalized vectors, let's put it that way, and I take a discretization of that curve, meaning that I partition the interval and I collect points there. Then if I take this distance between adjacent vectors, this is always greater or equal than this object here. What happens is that on the left side here, this depends on the representative of states that I choose, because if I multiply by a phase, this thing changes. But this here is depends only on the states. It does not depend on the phases that I choose for defining the states. And this distance here is the Beer's distance, okay? And I can then do the following, which is I make different choices for the phase and defining the same state. And then I can try to saturate this inequality for each of these values I. And if I do that, what happens is that the product of all these phases gives you the parallel transport according to the Berry connection. This is a cool result. I mean, it's not. But more than that, if I take the fidelity between adjacent points and I start expanding, assuming differentiability of this curve, then I will obtain the Fubini study metric appearing here. And actually you can, up to a certain approximation, write as something like this. And if you recall the definition of the susceptibility, you'll find that, because it's the second derivative, you find that this equality holds. And so the susceptibility is nothing but the pullback of the quantum metric by the following map. To each G, you associate this projector. Okay, this is clear, right? So just that. Okay. But I can do a bit further. I can write the susceptibility in terms of the projector P associated to the state psi of G and its complement, which can always be written in terms of an orthonormal basis for that subspace. And then you have an expression like this, okay? And if you go further, which is if this family of states is actually a ground state of a family of Hamiltonians, then this corresponds to a sum over excited states, okay? And then you see that this, for those of you familiar with perturbation theory, this is a second order perturbation theory formula in which you have the energy denominators and you have this numerator here. So you see that if the gap closes, this is potentially divergent. Of course that you have to see how this behaves, but you see where the things can come up, okay? Okay, this is what I wanted to say. And if you consider more general states, mixed states, density operators, then you can define the fidelity between two density operators given by this formula. Okay, and associated to it, the same constructions that I did. So the fidelity gave me the notion of Berry connection, gave me the notion of the Bierce metric. These same constructions will give you similar geometric objects in the relevant bundles.
For two states, the fidelity is just the scalar product.
Yes.
And it's based on the fact that there exists like a scalar product for two states. So do we have something?
Yes. So what happens here is, for simplicity, let us work in the finite dimensional realm, because otherwise it becomes a bit trickier. But the idea is that you take, suppose that you take a density matrix which has rank k, okay, and you're working in Cn, okay. Then you can always find a matrix W, which is n times k, okay, such that rho is W dagger, okay? And you see immediately that there is a gauge ambiguity here by taking W times U, where U is a unitary U in U of k, okay? And what happens is that the scalar product that you have on pure states, which was psi prime, then you have the same scalar product structure on these W's. It is the trace of W dagger W prime. Okay, this defines you, because essentially this W can be seen as a purification of this density matrix.
What's the name of this decomposition?
This decomposition, I don't know if it has I guess it's the purification procedure. And what happens is that this, for a fixed rank, this defines you a principal bundle with structure group U of k, and in that principal bundle you have a connection, which is the Uhlmann connection, and all of these things behave very well, just like they did in pure states. Of course, if you go back to rank 1, then this definition collapses to that definition, and everything is what you used to know. Okay, so this is what I was basically saying there. And then, of course, you can try to define quantities to probe this Uhlmann connection, and one of them that we chose was the difference between the fidelity and this trace here. And if you take a curve of density operators, it turns out that this delta, for small delta t, measures the non-triviality of the parallel transport with respect to the Uhlmann connection. So it is, in some sense, a way to capture these quantities. Okay? So now I move to the results. I guess this for you is a bit more boring. But essentially, the thing is that we use this approach to study phase transitions, and basically to see how these behave with respect to temperature. Because you've seen, I talked to you about these topological phases, and people know these topological phases are very important nowadays in physics because of the behavior. Because if you have a topological phase and you perturb it a little bit, as long as the gap does not close in that prescription that I was telling you about, all the topological features are invariant. Namely, those topological invariants stay the same. This is because it is a topological invariant. And the thing is that these special phases of matter come with another ingredient, which is that of the bulk-to-boundary correspondence. Because here, when I wrote the Hamiltonian, which I already raised, we considered it to be an infinite space. So it was an infinite lattice in Z2. But if you take this system in a finite size, because you cannot deform a topological phase with some topological invariant to another topological invariant, you say that you have Chern number nu in one place and nu prime in another, you would necessarily, to form one into another, have a discontinuity on these matrices. And what happens is that by taking the system size to be finite, what you're doing is actually truncating the system to the vacuum. Okay? And what happens is that there appear edge states, which are basically states which have zero energy, and they are strongly localized in the boundary of the system. You can do a simple calculation and understand how these things emerge. The thing is that if you go to a field theoretical description of this, what you get is when you probe the system to an external field, you get, by integrating out the fermions, you get the Chern-Simons theory. And the coefficient of the Chern-Simons theory is precisely the Chern number that appeared there. Okay, so there's a lot of cool things. And the thing is that we were wanting to probe these things with respect to temperature and understand how these things behave. So the methodology that we applied in this work was essentially to study the fidelity and delta on thermal states of this form, where beta is the inverse temperature. And the set of parameters that we are probing the theory with respect to is the parameter driving a quantum phase transition at t equals 0 and the temperature. We did some numerics here. We evaluated the fidelity and delta, and in which rho prime is obtained from rho by a small deformation on the coupling, or on the temperature, or on both. So in here we analyzed paradigmatic examples of topological insulators, such as the Kreutz-Ladder and the SSH model, which are in 1D, and also superconductors. So this Kitaev chain is very famous because it's an example of a topological phase in which the gapless excitations that I was talking about by the bulk-to-boundary principle are Majorana fermions. So people were very excited to see that it is possible in condensed matter systems to realize Majorana fermions. And we also studied the BCS theory of superconductivity. And because we don't have much time, we'll focus on this model and this other model. The results are very similar. So the Kreutz-Ladder model is a Hamiltonian of quasi-free fermions on a lattice, where you have two flavors of fermions, the A's and the B's. You have this space here, which corresponds to a discrete gauge field. And you have K, that is a hopping amplitude, and M. Okay? And if you fix 2K equals to 1 and phi to pi over 2, then you have a very simple phase diagram. And you can understand where the topology is if you consider the system on a line. You do Fourier transformation, and you see that there is a topological invariant, which is actually a winding number, because you see this model is again of that form, d of k dot sigma, and there is an extra symmetry which imposes that this vector, the normalized vector, is on the equator of that sphere. And then you have, and since k is one-dimensional momentum, it is on a circle, and then you have a map from a circle to a circle, and these are homotopically classified by integers. So it is quite easy to see. In fact, what matters is not the integer, but actually e to the I pi, that integer, which is the parallel transport of the Berry connection along the one-dimensional Brillouin cycle. And so this is the reduction model 2 of that invariant, okay? So in that case, if this m is greater than 1, you're in a trivial regime, meaning that this phase is 1, and in this, you're in the non-trivial regime, meaning that this phase is -1, okay? Of course, there is the bulk-to-boundary correspondence. If you consider the finite size chain with open boundary conditions, you have edge states. So these are the results. As promised, you see that the fidelity is having this it decreases drastically in the point of phase transition for m equals 1 and temperature 0, meaning that plane here. And as you increase the temperature, these features are smeared out. So this is the fidelity with respect to a variation on the parameter m. So this is the parameter that drives the phase transition at 0 temperature. Then you have delta, which recall that delta was capturing the non-triviality of the Uhlmann connection, the parallel transport with respect to Uhlmann. You see that delta is capturing again this phase transition at t equals to 0. And then you have, we probe the fidelity with respect to a variation in the temperature. Recall that the temperature appeared in the density matrix on the exponent of the Boltzmann factor. So it was something like this, okay? And so, when you make a variation of the density matrix with respect to temperature, you clearly still capture the phase transition, but we omitted the plot for delta, because what happens is that delta is constant equal to 0 with respect to a variation in the temperature. And I will explain why this is happening.
How did you compute for that? How did you compute that?
How did I compute this?
Yes.
So you take the system, you take the lattice with a finite number of points. You compute the fidelity, which becomes a product on this finite number of points, and that's essentially it. And you make a variation. You make variation delta m and delta t to be very small. Okay, so this is how it works. Of course, that you have to see how this behaves with the number of sides. So essentially, if you put, you have to see that this behavior is consistent as you increase the number of sides. Of course, in the thermodynamic limit, the fidelity between very close states goes to 0 because of Anderson or orthogonality catastrophe. And that's why in the thermodynamic limit, you need to study the susceptibility to understand the things. But in the finite size limit, it is well defined. Okay. Okay. So for the BCS theory of superconductivity, you have this Hamiltonian here, where epsilon of k is the spectrum, mu is the chemical potential, C and C dagger are creation and annihilation operators of fermions. And this is written in momentum space. Delta is the superconducting gap, and delta star is the conjugate. Of course, that this theory here comes from considering a mean field approximation of an interacting theory, meaning that these deltas here are actually determined self-consistently, and you have to be careful because they actually, when you turn on temperature, they depend on temperature, okay? So the results here are very different. So you have the phase transition at t equals 0, but then you see that this phase transition appears and drifts with temperature. The position of the phase transition drifts as V was the lattice, was the parameter driving the phase transition at t equals 0. And you see that if I increase the temperature, you see that the critical parameter of V is changing. So this is what we call a temperature-driven phase transition. And here, all the quantities are non-trivial for variations both in V and both in T, meaning the temperature.
What was the physical meaning of the V?
The V, so in the topological phase, you have M, which was probing the phase transition, and V was is the parameter which, as you change it, you observe the quantum phase transition. A quantum phase transition is, by definition, a transition that occurs at temperature 0. So as you, so the V has the same role as the M in the other theory. Okay.
Okay. But what is the role in the BCS theory? It has to do with
V. So essentially, the original theory has a Coulomb interaction. which is and essentially the V has to do with the exchange of a phonon in a.
That's to do with the strength of the Hooker pair, or?
It is related to that, yes, in some sense. Yes.
And you said also the analogy with the M in the previous case, but you fix the K and move the M, but wouldn't you also do it the other way in the previous model?
In the previous model, so you don't lose. What happens is that so you fix this hopping amplitude K, and as you vary M, you see a quantum phase transition. But this was a choice that we take. But other choices would lead to different diagrams in M, I guess.
Just K and M, you have a line.
Just K over M, not just the rational.
Yeah, I think it's actually a function of K over M. Yes, yes,
So
you're right.
Multiply the M.
Exactly, by scale factor. Okay, so I'm just going to give you a rationale why you still see variation on delta for this case. And the reason is the following. Density matrices are Hermitian operators, and therefore they can be diagonalized in a very straightforward way, right? And essentially, if you make an arbitrary variation of the density operator, you have a variation in its eigenvalues, D, and then you have a variation in its eigenspaces, which is given by this commutator formula. And essentially, well, this is trivial statements, but the thing is that, as you saw, when I change the temperature here, the eigenspaces of this density operator, they are not changing, because the eigenspaces of rho are the same as that of H. Okay, so variations in temperature do not change the eigenspaces, and actually the topological features are encoded in the eigenspaces and not in the eigenvalues. Okay, of course. If you change one eigenvalue to 0, then things become drastic. But with temperature, you're just smoothly changing the eigenvalues of these.
So this is true as soon as the temperature is always finite.
Yes, exactly. For finite temperatures. So this is a table which basically resumes this what is happening there. So the variations on the spectrum lead to variations in F, but not in delta. Variations on the eigenspaces lead to variations in everything. Why did delta have a variation in the BCS theory of superconductivity? Because then the Hamiltonian depends on temperature, effectively. Because you're considering a mean field description in which the parameters of your theory depend on temperature. They are self-consistently generated. So this is the reason. Now there is something which is non-trivial for me still, which is when you're considering all these studies, you're essentially considering a bundle over a space of parameters, okay? And the behavior of these bundles as you change the parameters is what basically tells you the topological features. But there were some previous studies in which they were studying approaching the Uhlmann phase along a one-dimensional momentum cycle in the space of parameters, and they seem to have a phase transition with temperature, which here we say there isn't. I would like to argue against that in the following case. So if you consider the integer quantum Hall effect at 0 temperature, what happens is that the topological invariant, which is associated to the gap theory, appears in the form of a response function. So if you probe the theory with respect to a gauge field, the topological invariant appears in the response of the theory. So it is, however, unclear that the Uhlmann phase, the Uhlmann allonomy along the one-dimensional Brillouin zone, has some kind of meaning in terms of the response of the theory. So if you put an external field, does it pop out as a response function, as a susceptibility, as some kind of correlation function? I don't know. This is something which... so this is a way to defend that for us, there is no phase transition as a function of temperature. Okay, so then there is the other, I don't know how I am on time, but essentially the other work is on regarding dynamical phase transitions at finite temperature and the associated, basically, susceptibilities. So let me tell you a bit about this. So if you have the real-time evolution of a closed quantum system out of equilibrium, there are some similarities with the thermal phase transitions. Basically, the analogy goes as follows. In thermal equilibrium, you would diagnose a phase transition by seeing some non-analytic behavior in this free energy. And here you have, in the real-time evolution of a quantum system, you have this overlap where you do a sudden quench with respect to a different phase with this Hamiltonian edge, and then you can define this dynamical free energy. So this is a sketchy way to put it. And if you see some non-analytic behavior on this G in the thermodynamic limit when n goes to infinity, you say that you have a dynamical phase transition. Moreover, if this state here becomes orthogonal to that state here, then of course this goes to zero and this explodes, and these are the so-called Fisher zeros in the literature. So let me be a bit more technical. So let's take a family of Hamiltonians parameterized by perhaps a manifold, a smooth manifold, and suppose that H is smooth, and take two points on this manifold, lambda I and lambda f. Then the Loschmidt echo at time t is the following quantity. So it is the overlap between the initial ground state of in parameter lambda I and with the quenched state given by this Hamiltonian taken with respect to a different point here. Okay, so you take 2 points. Of course, if lambda f goes to lambda I, this is trivial, and you see how this behaves as you separate lambda f and lambda I. Of course, for this formula to be well defined, you assume that this is a ground state and it is non-degenerate, at least generic. So what you can do is the following. You can take this unitary evolution operator and you can do as in perturbation theory and make an expansion like that. So you say that this evolution operator is equal to the n-perturbed 1 multiplied by this Dyson series, you see. Where V is essentially, it has to do with the difference between the Hamiltonians in the interaction picture with respect to the initial Hamiltonian, okay? It is now clear, if you take this formula here, that this expectation value, this Loschmidt echo, can be written as such. And now what you can do is to develop perturbation theory around this formula. So if we take parameters which are close by, then V can be approximated by this, where this is exactly it has to do with the tangent directions, okay? So what you can show is that this Loschmidt echo has to do in second order. It has this form where this susceptibility is now given by a cumulant, okay, with respect to the original ground state of the theory, okay. So you see that this is what you're supposed to get. But now it depends on lambda, but it also depends on t because you're having this quench on time. This is what we call the dynamical susceptibility. And of course, we can relate this to a pullback of the quantum metric because after all, the Loschmidt echo is nothing but the fidelity between two states. Actually, between the ground state of the theory and the quenched quench state. And if you recall from previous arguments, the relation between the fidelity and the Beer's distance and the Beer's metric, you see that essentially the dynamical susceptibility is the pullback of the Fubini study metric by this map, actually by the projector associated to that. Okay. So this is interesting. And now what can we do at finite temperature? At finite temperature, you don't have pure states. You can then consider the fidelity between the states, the thermal states like that, and those quenched. Okay. So of course, that now the evolved density matrix is by acting through conjugation by the unitary evolution operator. And this is what we call the fidelity Loschmidt echo. And of course, the associated susceptibility is the pullback of that Beer's metric in the space of Uhlmann density matrices, but now by this map. Okay. So, but what you can do differently is that if you recall that at zero temperature the dynamical susceptibility was given by this cumulant, then you can naively replace this average by the average on the thermal state associated to the initial phase. And then you get a different generalization, which is that. Okay? So it is this trace with the thermal state here, and then you have this interaction picture evolution potential. Okay? This is a different type of Loschmidt echo. Of course, the two definitions that I gave you, one which is the pullback of the Beer's metric, and the other which is given by this cumulant, at zero temperature, if you take the limit t to zero, they both coincide. But the thing is that this other susceptibility that I'm talking about now is different in nature because it can also be seen as a pullback of a metric, but not in the space of states, but in the space of unitary processes. And the way you see this is through the following proposition. If A and B are linear operators on a Hilbert space, it misses something here, and rho is a full rank density matrix, of course then this becomes an Hermitian form in the space of linear operators. And with this Hermitian form, you can use it to build a metric in the space of unitarities, which is a Lie group, and you can put the metric associated to this, where rho is taken with respect to the thermal state of the original phase. And then when you do this, you understand that that different susceptibility, the interferometric susceptibility, is a pullback by this map. Okay, so it's all of them can be seen as pullbacks, but one is in the space of states, density operators, and the other is in the space of unitary processes. So it's kind of different. Okay. Well, this is a physical interpretation of the second susceptibility. You can actually try to see how you could see this in the lab. But the thing is that for the theories we're considering, you would have to put a many-body density operator in an interferometer, and this is a bit pointless. So you can do the calculation and see that this has the same form as the interferometric Loschmidt echo, and this would be how you would compute. Then we have some results for two-band systems, and essentially the two susceptibilities are very different, because you see, if you take the Hamiltonian to be of that form, then by taking the tangent vectors of the associated the push forward of the tangent vectors, you see that there are directions which are tangent to a sphere of constant energy, and those that are normal to that. And essentially, these tangent directions, they change the ground state of the theory, and the normal directions, they just change the eigenvalues. And the thing is that the Fidelity Loschmidt echo, it only sees the change in the state. And the reason is that when you act upon conjugation on a matrix, you don't change the eigenvalues. You just change the eigenspaces. And you see, this is the consequence of that. So one of them sees all kinds of variations, tangent and normal, and the other just sees tangent variations. Moreover, you see that this envelope function, as a function of temperature, gets smaller and smaller, meaning that whatever phase transition that you see, as you increase the temperature, it gets smeared out. While in the other case, this is not true. Okay, this is what I wanted to say. But perhaps the most interesting part is that the difference between the two metrics has a relation to equilibrium. Because if you see that there is this factor appearing, and this is actually equilibrium susceptibility. So in some sense, when you study these non-equilibrium processes, you would like to give a relation to what happens at equilibrium, and it turns out that seeing, measuring the Loschmidt echo with respect to the states, and that with respect to the unitary processes, the difference between them has a relation between to the equilibrium. So this is what I wanted to say. Perhaps this part was a bit more boring, but I hope you enjoyed this.
Is a connection on the space of states.
Okay.
So, for example, in the case of the spin 1/2, at some point you said that the first Chern number is 1 or -1.
-1, yes.
So essentially, the Berry connection is a specific choice of the monopole bundle.
So the Berry connection is a specific choice of a connection in the monopole bundle. Essentially.
In this case, like monopole charge 1 or -1.
No. That is invariant. So it's a classical result from differential geometry that the characteristic classes, such as the Chern class, is invariant under the choice of connection that you use to. So it does not depend on that choice. However, the geometric features of the connection, of course, it's a choice, but the rest is fixed.
So you're already fixing the bundle.
So in that case, what we are doing is that we have. Let me put it in perhaps a more mathematical way to see it. CP1 is the set of lines through the origin in C2, and basically you consider the monopole bundle is simply the fiber at the line is the line itself, and essentially yes. And when we have a map from from a torus to CP1, we're pulling back this structure here, and there is a canonical construction. So you have a bundle over this, and what happens is that the Chern class here is basically the pullback of the Chern class that you have there. So in C of because the Chern classes are natural, so it's something like this, right? And from this, because this here is a generator of the cohomology of so it's basically it gives you a top generator, and essentially you see that the degree of this map is computing the Chern.
Okay. Yeah. So before.
So you don't need a connection. Yeah, you don't need a connection to calculate all these things. But the connection is a choice that comes from the fact that you give C2 an Hermitian inner product. Okay. because you're considering Hilbert space structure. Right?
Okay, so you're already making some assumption on what kind of bundle you're choosing, and then you will start doing everything.
So this construction is very natural, right? Because if I take suppose that let's see that perhaps this would be more interesting for you. So if I take those free fermion Hamiltonians, in general, what happens is that you have a family of Hermitian matrices, and parameterized by generally a smooth manifold. What happens is that there is a gap condition, and you can deform this matrix to be of the form locally. You can write this as something like this: identity k minus identity n minus k. Okay, s minus 1 of x. Okay, so you see the ground state of the theory is obtained by filling the bands here in this sector on the energy which is below 0. And what happens is that essentially what this is defining through this formula, so you can take S of x will be a set of vectors, v1 until vk, the columns are v1 until vk, and then you have vk plus 1 until vn. And these vectors are specifying an n minus k dimensional subspace of Cn. And over the set of subspaces of n minus k dimensional subspaces of Cn is a Grassmannian of n minus k. So it's gr n minus k of Cn. And over this you have a tautological bundle, which the fiber over a point here, which is a subspace, is the subspace itself. And over there you can define all this is a vector bundle. It's called the tautological bundle, and you can pull whenever you specify a family, you're specifying a pullback bundle with respect to that tautological bundle. I think it's kind of clear. I'm not sure.
Yeah.
So, okay. Oh, sorry. I tend to go. It's because I want to jump and. Thank you very much.